and 0.165 milliliter respectively. The unreturned species passes through the column is 3.1 minutes. A and B, we know the retention time of A and B, and their peak width. So what we can do. So question A is similar to the previous one. You can apply this equation, right? So plate height, we have n, so we can easily to get the h. So what's the retention factor of A? So we need to go back to the definition of retention factor, right? Here we just use time to calculate the retention factor. So this ABC is quite easy because we have enough information to derive the answer. So now go through the partition coefficient of A. So here we need to recall the definition. What is the partition coefficient? Also the distribution coefficient, right? The capital K. Capital K is have the relationship like this one, but during our study, we use this with their position. So with K equals K Vs over Vn, so we just flip their position. Okay, so we can get we have a volume, right? In here we have the volume. We have the volume and we have the retention factor, so we know we can get the partition coefficient. And we also call this distribution coefficient. And then we can still calculate the resolution through the retention time and the peak width. So this question are similar. So all the following questions are similar. So we can still use this simple relationship to calculate the new n number and the new length of column required, and also the new retention time we should have. Right, so it's easy. And the calculation like this, because this calculation is quite fundamental, so you should know how to do a question like this, and there are calculation questions in the exam, so you should be acquainted with all the equations and know the concept of this symbols. And here I listed all the all the formula you should remember in the right frame, inside the right frame. And this one, although I don't ask you to know how to write the exact form of this equation, but this relationship, the relationship between these two is very, very important. You must No, do not forget this. Okay, so when we from the spectrum we can do qualitative and quantitative analysis because the retention time. If we for one separation we for a certain column condition. Okay, so when we see the several different peaks, and in this case, each peak, if we only consider they have only one cellulose, so for those cellulose, why the cellulose is located at this time? It's because it's determined by the cellulose, the property of the cellulose. Okay, so if we fix the column condition, we the retention time of cellulose can bring us qualitative information. And the peak height or peak area of can bring us the quantitative information. So sometimes we calculate the area, sometimes we calculate the peak height. And for considering the band broadening, usually we calculate the peak area when we do the quantitative analysis. So if we want to know want to identify some peak, we want to know which molecule exists in your sample. You may use standard sample and run the separation at the same condition as your real sample. So if the column condition is fixed, ideally their retention time only reflect their molecular property. So the retention time should represent the molecule species. So if we only consider quite simple case, when you measure the compound B as the standard, you should say your sample, or if you can find the same retention time peak in your sample spectrum, you can see you find the compound B, because the standard one also have the same retention time in your sample. But you should already have question in your brain. So maybe maybe this identification is not accurate enough. Maybe just because we have not we cannot measure the retention time as accurate enough. Maybe some quite similar molecule have the same retention time. So the quantitative analysis just apply to some simple situation, and you have some background information for your sample. And in that case, you can do the quantitative analysis. So if you want to identify the molecular species in your sample, usually we use mass spectrometer as a detector. to do the quantitative analysis. That's the most powerful way. Also, we can use the NMR, right? But MS spectrometer is the most powerful way. And the following way is the quantitative method. And this part, I want to just have a quick go through of this part. I don't want to put too much time on this. And this part, I will note because this one is not related to the chromatography analysis directly. And this is a general principle of quantitative analysis. And this part of information will not appears in your midterm examination. So there are several different ways, and the most straightforward way is just to measure the peak area directly. So, but if you can, if every species in your sample have signal response, and you can measure each compound, the peak area percentage of each compound, and you can get the relative quantity. Of course, you need to assume all the species have the similar signal response. Okay, so this, and you can also, if there have no similar signal response, we can do some correction. And also, you can still do the quantitative analysis. Also, you can add external standard, and you build a standard curve. And if the two separation condition signal response are comparable, you can still do the quantitative analysis. Right. This, I think, so this is the general principle of the quantitative methods, and not only for the separation, the chromatography. Okay, sometimes we have sample matrix effect. So in this case, we need to build another way. We use the standard addition method. So the matrix effect can be supplied, can be surpassed, and we built a new standard addition curve and calculate using this curve. When we get the linear fitting equation, we can calculate when the equation, the y equals 0, we can get the x point here, and the absolute value of the x is concentration of your the targeted sample in your concentration will target sampling. So you can use this way. You just know there are several different quantitative analysis methods. Also, we can add internal standard. Okay. So, but for internal standard, this is a general principle. But for the chromatography, because they different molecules separate at different times. So for if you want to do the internal standard analysis in the chromatography, you need to choose the molecule have a similar structure or similar elution property to your targeted molecule. For example, in this example, we use the glucose. We use we use the lactose as a standard, and the target is glucose. Right. So because those two saccharide are similar, so they have similar retention time. Also, we can use S-topic labeled internal standard, but in that case, you cannot distinguish the internal standard and your sample through the column because there's no chemical difference between the S-topic labeled chemicals and the normal chemicals, but you can do the separation through the mass spectrometer. So that's another way. So this is not the core information I will not cover in the examination. Okay, now let's start to the section 3. Gas chromatography. So the part 1, this is part 3. So part 1 and part 2 is it talk about the general principle. Those principles apply both to gas chromatography and liquid chromatography. And liquid chromatography will be introduced by Dr. Hu, and she will also introduce the deeper and more detailed theory, and I introduced previously, but we because in this class we split the method so by 2 parts. One is GC and one is LC. So we need to learn the principle 2 times, but in different level, right? So in the second part, you will learn a more complex theory. So the GC is we are using the mobile phase. You're using the gas as mobile phase. So even though the mobile phase is gas phase, it's still the chromatographic process. So it is still a partition between 2 phases. So no matter what type of matter status we have. So this is introduction. So it's better to see the video. Okay.
Gas chromatography, GC, is a method of separating mixtures and is particularly suited to mixtures of fairly volatile liquids. As in all chromatographic methods, there is a mobile phase, in this case a gas, that carries the components of the mixture over a stationary phase. In this case, the stationary phase is a tube called a column, packed with solid or coated with a high boiling point liquid. The components of the mixture leave the column in order of volatility, the most volatile first. This is the complete instrument, with the computer control system on the right. The sample is injected here. From this injection port, the sample passes into the column, which is kept in a temperature-controlled oven. Columns are normally wound into a spiral to save space. This capillary column is 30 meters long. This is much shorter, about 1 meter. The properties of the column and its filling are chosen for the particular separation that is to be carried out. The components of the mixture are carried through the column by a stream of inert helium gas, the mobile phase. The more volatile the component and the less it interacts with the stationary phase, the faster it travels through the column. At the other end of the column is a detector that detects each component of the mixture as it comes out of the column and also measures its amount. This instrument has a flame ionization detector, which consists of a hydrogen flame burning in air. As a substance leaves the column, it burns in this flame, producing ions, which can be detected by measuring the electrical conductivity of the flame. The hydrogen for the flame comes from this cylinder here. Before beginning a separation, the operator must set the flow rate of the gases and the temperature of the oven. The temperature of the inlet port is also set at a level that ensures that the sample is fully vaporized, and the flame ionization detector must be lit. Here, we will separate a mixture of methanol and methylbenzene. About 0.1 microliters is taken up in a hypodermic syringe. It is then injected into the inlet port through a self-sealing rubber disc called a septum. The first peak is methanol, the more volatile component. Its retention time, that is the time taken for it to pass through the column, is about 1 minute. The second peak, with a retention time of about 1.5 minutes, is the less volatile methylbenzene. Its peak has a larger area, showing that there is more of it in the mixture. The computer calculates accurate retention times and peak areas. The area under each peak is proportional to the amount of each component. The computer calculates this. This instrument is used for undergraduate practical sessions, and samples are run singly as and when each student is ready. In this alternative instrument, the gas chromatograph is on the left, and the detector is a mass spectrometer, which runs the mass spectrum of each component as it comes out of the column. This can be particularly useful when analyzing an unknown mixture, as the mass spectrum can help to identify each component. The combined technique is called gas chromatography mass spectrometry, GCMS. This GCMS instrument has an auto changer for the samples. Many samples can be loaded up and run automatically, perhaps overnight.
So we know the basic process of GC analysis, and this is a different part, and looks similar in the video. Okay, so still here we usually have some core part. One is the carrier gas, and then use the flow controller to achieve a certain flow rate of mobile phase. Then here is the sample injector point. And after injection, we will release a signal to the computer. So from this point, we record the time as 0. So the unwritten sample goes through the column and reach the detector. And this signal, the time when we detect this signal is unwritten time, TM. And all other signal from the sample, because they have a certain retention, so they are all the time are retention time. So those are similar ones. So they just use the different charge, but usually for one analysis, those information are crucial for when you study others method. So we should know the flow rate and which type of the column they use, and the mobile phase, and the oven temperature. For DC, we usually use a temperature controlled program, and which type of detector we should use. So we should consider this. So now we can study the instrument system part by part. So now let's see another video.
Here, one quick biochemistry basics here. Let's talk about gas chromatography. Gas chromatography is a chromatography technique used for the separation of volatile compounds. Volatile compounds are the compounds that gets easily vaporized at room temperature. Let's see the components of gas chromatography. The column. The column used in gas chromatography is very long and arranged in a coil. The column used in gas chromatography are of two types. Number one, pack column, and number two, capillary column. Pack column. Pack column can be made up of glass or stainless steel. The length of this column can vary from 1 to 3 meters and has an internal diameter of 2 to 4 millimeters. The capillary column. The capillary column is made up of fused quartz. These columns are very long and have length from 10 to 100 meters and have an internal diameter of 0.1 to 1 millimeter. The column is placed in a chamber so that a uniform temperature can be maintained. The stationary phase. The stationary phase is packed in the inner wall of the column. The stationary phase is made up of silicon grease or wax, which can withstand a high temperature. The mobile phase. The mobile phase use is usually an inert gas like helium or unreactive gas such as nitrogen. The mobile phase gas is kept in a cylinder which is connected with the column via molecular sieve. The molecular sieve separates the unwanted hydrocarbons, oxygen, and water vapor that may interfere with the test sample during analysis. At the end of the column, there is a detector which detects the sample. Let's see the working of gas chromatography. The sample which is to be separated is mixed with an appropriate volatile solvent such as heptane, acetone, or methanol. Just before the column, there is a septum that allows injection of the sample. The temperature of the injection region is kept 20 to 50 degrees Celsius high as compared to the column. This allows rapid volatilization of the sample. Once the sample is volatilized, it passes down the column where the separation occurs. During analysis, the temperature of the column is kept between 150 to 300 degrees Celsius. Separation occurs based on the interaction of molecules between the mobile phase and the stationary phase. The less volatile molecules interact more with the stationary phase and move slowly, while the more volatile molecules interact more with the mobile phase and moves fast down the column. Once the separation is completed, the detection is done with a detector attached at the end of the column. One of the most common detectors used with gas chromatography is flame ionization detector, or FID. The flame ionization detector has 3 inlets. one for the carrier gas, which comes from the column, and the other two for hydrogen and oxygen. The igniter ignites hydrogen and oxygen to produce a flame. When the sample molecules reaches the flame, they get ionized and the electrons are released. Across the flame, there are two electrodes, each with a positive and a negative charge. The electrodes detect the electrons generated by the ionization of the sample. Electrons are detected in the form of current, which is amplified and detected by the computer. When the sample is detected, the computer gives a peak with respect to the retention time of the sample. The area under the peak gives information about the concentration of the sample. If the concentration is less, the area under the peak will be less. And if the concentration is more, the area under the peak will be more. Now, for the detection of unknown samples, we need to have standards. Let's understand this with an example. Suppose we run methanol as our sample and the peak of methanol is obtained at 5 minutes. Next, we run acetone as our sample and the peak of acetone is obtained at 3 minutes. Next, we run unknown sample and we get this chromatogram. Now, using information from the standards, we can say methanol is present in the unknown sample, whereas acetone is absent. The remaining peak is still unknown as we do not have any standards to compare its retention time.
Okay, the first part, the carrier gas. So in GC system, we call the mobile phase, usually we call it as carrier gas. So this is a instrument for the carrier gas supply. So we have the gas cylinder to store the high pressure gas inside the cylinder, and we have the pressure regulator to control the flow rate, the first stage of the flow rate. But to get the the accurate flow rate, we need second stage controller. So here we have the flow meter and the flow controller. So this is the first stage. We can control the rough flow rate of carrier gas to meet the requirement of GC separation. But the flow rate is quite important parameter for the separation. So we need a flow controller. So for your real work, even though I labeled it not very important, less important slides, but it may quite help you for your real work. So there are a lot of slides labeled less important and have many detail. But I will also have a brief introduction and also for your reference in your real work. So different carrier gas have different colored or labeled gasoline for the storage and for storage, and you can read the color code to identify them. And they also have wide range of size. So here is above the cylinder, there is a cylinder valve. So this one just serves as gas stopper because you cannot regulate flow rate through this valve. You know there are screws here, but they just behave like on off switches, so you cannot control their flow rate. So if you want to control the flow rate, you should connect the gas regulator next to the cylinder valve. So there are many different types of gas regulator, and to meet different type of gas. So here is a video to show the detail.
This is an introduction to pressurized gas valves and how to take care of them properly and how to use them properly. There are 3 specific valves. This one connects to the tank. This one allows the regulator to work, which is going to go from tank pressure down to pressure that you can actually control. And this knob down here will actually allow you to release it into whatever device you want, for example, a balloon. So let's go through it. You'll notice that when you get started, this is closed and locked in position. This is opened all the way up, and this one is closed. Now, what is open and closed? Well, first off, when you open this, watch the valves and the gauges. You'll notice that when I opened up this tank, this pressure started to read. But you'll notice that even if I open this up, no gas is coming out of it and there is no pressure change, because right now, this valve is not allowing any of the gas to go from here to here. To allow that to happen, turn this knob and screw it in. And when you screw it in, you will notice that the pressure is now going to start to read over here. Once you notice that the pressure is reading over there, you can start draining it out of this container. And now you're draining it at a controlled or a regulated rate. So now let's say you go ahead and fill up your balloon or whatever it happens to be. You lock that off. Now you're done. What do you do to turn everything off? 1, turn off the tank first. 2, make sure that this is open enough that it can actually bleed the valve, because right now there's still too much pressure inside of this portion. Open this all up, drain it, close it, and then reopen this so that way the gas, when this is open, it's not just going to automatically come out. If you have any other questions, please ask someone you think knows how to use it.
So here it shows some structure and principle of the needle valve, how it works.
Before working with fuel gases or oxygen, be sure that an approved fire extinguisher is readily available. Ensure that the cylinder is properly secured. In Chicago, cylinders must be chained to the wall. In Evanston, cylinders may be secured by bench straps, floor stands, or chains. Remove the cylinder cap. Remove debris from the cylinder valve. Inspect the regulator and gauges for damage and debris. Look for defects that may allow a leak at the connections. Do not connect parts that appear to be damaged. Remove any debris with a clean, dry cloth. Attach the regulator to the cylinder valve outlet. Never force the connection. If the inlet of the regulator does not fit the valve outlet easily, it may indicate the regulator is not intended for use with that gas. With a smooth-jawed wrench. Turn the regulator's pressure adjusting screw counterclockwise until it turns freely. Open the cylinder valve slowly until the inlet gauge on the regulator registers the cylinder pressure. If the cylinder pressure reading is lower than expected, the cylinder valve may be leaking. With the flow control valve at the regulator outlet closed, turn the pressure adjusting screw clockwise until the required delivery pressure is reached. Leaks can be detected by performing a pressure test or a bubble test. To perform a pressure test, close the cylinder valve after checking the regulator's function. If the pressure on the inlet gauge remains steady, there are no leaks. To perform a bubble test, use an approved bubble solution such as Snoop. Apply the solution near the inlet connection, the outlet connection, and the valve stem connection. If there are no bubbles, there are no leaks.
Okay, so when we release the gas solvent needle valve, so we should know measure the flow rate, because through the regulator we can only read the pressure. So how about their flow rate? So we need another one flow meter to get the number. So this is not a simple one. Here's the gas flow from the regulator. The gas below above a bubble, right? And this one, this is after we watch this video, we can start finish today's lecture. So this one's much quick.
I need to go drink some water.
So because we can determine the volume and we have the label here. So when we count the time, we can calculate the flow rate. This is quite simple and also very accurate. So in the next lecture, we will introduce some other type of flow. We will flow controller or flow meter.